although this learning sequence was a little bit theoretical, a lot of theory, we still have something to practice. So let's start with, let me show you how to make a histogram distribution, histograms for frequency, for relative frequency, for density, and then also let's discuss a little bit the use of uniform distribution. I make a new script. I'll call it lecture 12A. And then let me just reuse the data set for this sample of 10 apples with sugar content, as I used also in the previous learning sequence and also in this video, at the beginning at least, right? So if you want to make a distribution histogram, the easiest way to do that is to use a function hist. It computes everything automatically and shows you the histogram. It also automatically finds the breaks for the beans, so it finds the splits and boundaries of every bean and so on and so forth. So you can see that this histogram looks a little bit different from what I have shown you because I use different splits. I'll show you in a minute how to make splits manually, how to enter splits manually. Well, first of all, you can actually make a recommendation. So in this case, you can see there is 5 splits. You can try to recommend, for example, using 4 splits. But the problem is you can see that in this case, R didn't follow my recommendation because it always tries to find the best number of beans, the best number of splits. So in this case, 4 and 5, the R favors 5 to 4. If I say 3, then it's the same. If I say, for example, 6, you can see it doesn't change anything. 8, now it changes. This is a little bit annoying because it doesn't follow the recommendations, right? It just tries to find the best value around the one that you recommend to use. This can be fixed if you provide the breaks. So if you say X, and then you provide the breaks as a vector. So let me show you how to do that. And then you simply provide the breaks as a vector. For example, you start with 8.8, and then let's say 9.3, 9.8, 10.2, then 10.6, and finally 11.1. For example, just an example. So now you can see it looks a little bit more like what I have shown you. And then you can see by default it uses density. It's a density distribution histogram. If you wanted to make a frequency distribution histogram, then you need to say frequency equal to true, and that will be the frequency. Now you have counts. You can see this is 1 value, 2 values, 4 values, and so on and so forth. And then if you say freq equal to false, then it will be density. Okay. What else? As you know, first of all, you need to compute all these values. You need to compute counts, you need to compute frequencies, densities, and so on and so forth. And R does it for you. This function hist does it for you. But you actually can get, similar to boxplot, you can get all the calculated values and save it to a separate variable. For example, let me use P here. And then you can see P is a list of 6. And inside this list, you can see the breaks, automatically computed breaks, then the counts in every break, densities, and the middle points. So strictly speaking, you can even make your own plot. For example, you can say plot $P meets, it's the middle points. Then $P, for example, counts, $P counts. And then, for example, type equal to B. And then you will see it like this. Okay. You can even actually add something on top of it. So you can say hist first, and then you can say lines. And then it will add the lines on the top. You can, for example, make them red, equal to red. I don't think it makes sense, actually, just to show you that it's possible. So you get all the calculated values. In this case, you can see it's counts. But if you, for example, if you say P hist density frequency equal to false, it will be the densities. And then here you also need to use density. So now you can see you have the same for densities. Okay. We will use this later when I'll show you how to, for example, show the theoretical histogram on top of the empirical distribution. Okay. Now let's talk about uniform distribution. I told you already, or you know already, that there are 2 functions. Let me just make a uniform distribution, which you can use for calculations. One function, it's punif. It's a calculation of probabilities. It's CDF function, cumulative distribution function. And then just to repeat an example, for example, we would like to compute a probability to get, for example, $800 or less in win, and then the minimum win is 100 and the maximum is 1000, and that gives you 0.78. It's exactly what I have shown you before in the videos. And then Q unif, it computes a value for a given probability, for example, first quartile. So this is how to compute first quartile. Okay. R has two additional functions. For any distribution, it has four functions, in fact. The function D unif in this case, it's a density. So you can compute density. For example, you can write 800, 100, 1000, and this will be a density for this particular value. Okay. What you can do, you can actually do the following. You can compute a sequence of all values, let's say starting from 0 and ending with 1200, and then let's say by equal to 1. So it will be like, let me show you how it looks like. You can see it simply values like whole numbers, 0, 1, 2, 3, 4, 5, and so on. Then you can compute density. You can say D unif, uniform distribution density. Let me remove this one. X, and then the parameters of distribution, 100 and 1000. So it will compute density for every value in X. You can see that F has all these density. You can see density is 0 because you remember we start with 100, and everything below 100 or above 1000 will have density 0 because it does not exist. It's the smallest and the largest value. And then you can make a plot. We can make a plot, XF. Let's make it red. So this is the density distribution, right? So I need to make it a line plot, type equal to line. So this is the density distribution. You can see indeed density is 0 beyond the range, beyond the 100 and 1000, and then equal densities within this range. So this is probability density function for uniform distribution. Now there is one more function which is called R function, R unif. R function, it's a random value. It's like if you take a sample from this population, for example, 10 values between 100 and 1000. Right? Let me show you. So this is it. So for example, if you roll this fortune wheel 10 times, so that probably outcomes that you can get, right? So you can see 944, 679, 627, and so on and so forth. So in this case, you can see they are decimal. They have decimals because distribution, it's a continuous function. It's not a discrete function. But what you can do, you can actually save it. And then, for example, round the values, right? And then you will have the whole numbers like this. Okay. Let me take 100 values, 100 random values from this distribution. And then let me show you how it looks, the empirical distribution. So this is the empirical distribution. And you can see that despite the fact that we got this as a random sample from this uniform distribution, you can see it's not ideally rectangular, right? Because it's a sample. It's a sample of size 100. It always will deviate from the theoretical expectations, right? Now, what I can do, I can actually add the theoretical function. I already calculated the theoretical function. What I need to do, I need to make it, you can see it's frequency by default. So I would like to have it a density, frequency equal to false. So now you can see it's density. And now I can add these theoretical functions that I computed, lines. You can see X. Let me just use another variable here. Let me use XX here. Okay. Why I do it? Because I want to keep this X. So let me run this first again. So it works. Now let me run this one. It works. You can see now it's different because I took a new sample. So every time I run it, I will get different sample. You can see it varies because it's a random. It's just a random sample. And sometimes you can see the values are far from the rectangle. But let me add the theoretical function now. X, F, and color equal to red. And let me also make it thick. So this is the theoretical expected value. So in theory, all these bars should be close to this red line. But in practice, let me run it again several times. You can see they deviate, of course. And the smaller sample size, the more deviation you will observe. So this one, almost perfect. But sometimes you can see the deviation can be quite big. But if you have a large sample size, let me take 1 million values, for example, right? So this is 1 million values. Then you can see it will be almost perfect. So once again, all the theoretical distributions, they describe situation when you have almost infinite sample size. In this case, the empirical data and the theoretical data will match almost ideally each other. But when you have a sample size smaller, let's say, I don't know, 10 values, right? So in this case, you will see a clear discrepancy between the theoretically expected values and the sample values. But again, it doesn't matter because you still can estimate the parameters of your theoretical distribution. For example, in this case, if I calculate mean, you can see it's 158. It's not 100, but it's pretty close to 100 comparing to the whole range, right? Again, max, you can see max, it's 998. It's very close to 1000. And of course, every time I take a new sample, these values will be different. But you can see that the magnitude is very similar to the expected values, right? So you can see that this is always around 100 and this is always around 1000. A little bit less sometimes, a little bit larger sometimes, but it's pretty close. Okay, so even if your sample size is 10, you still have a pretty good estimate of minimum and maximum of the parameters of the distribution. Okay. More about how big the discrepancy is between the real parameters of your theoretical distribution and parameters that you estimate with the sample, we will discuss in block number 2 when we talk about inference. But right now we can just see from all these simulation examples that actually estimates also not very precise, but they are good enough. And then, for example, if I have a sample size of 30, then you can see the estimate will be much closer to the real ones, right? So you can see that it's some of the estimates are pretty good. And remember that histogram, you should trust histogram only if you make it for a large sample size. Even 30, you can see quite a big discrepancy. But for example, for 100, most of the time, the histogram will look pretty good and pretty close to the theoretical distribution, right? You can, of course, make also this plot for percentages. So you can say that, for example, xx sorted equal to sort xx. And then you can calculate the percentages. Let me just use xxp. It's we need to generate the sequence of between 1 and length of x. Then we subtract 0.5 and divide to, let me actually define n as a length of x. So for the sake of simplicity, and then that will be much simpler, this one. So I can put percentages like we did in learning sequence 1. And then I can make a plot, this percentages plot. Let me see, 1n. This one is obsolete. This one. Now it should work. Yes. Now I can make a plot, XSS, XSP. So this is the percentages plot. You can see it. And now I can actually add the theoretical line. First of all, I need to compute it. I use like P theoretical is P uniform distribution, CDO function for uniform distribution. And then I will use these X values that I generated before. You can see from 0 to 1200 X and then 100 and 1000, right? And then I can add it as a line, X and PT, color equal to red. Then you can see, let me see, lines. Then you can see again a very good fit. So this is theoretical function. This is the empirical data we got using this RUnif function. So it's random sample of 100 values taken from the population, and you can see it's a good match between the theoretical values and the randomly taken sample. Again, if I change it to 100 and let me run it to 10, to 10, and you can see that. And then let me just change these two. Otherwise, I think here I need to use XX. Now let me change it to 10. And you can see that it will be a quite bigger discrepancy. Sometimes the fit is good. Sometimes the fit is not very good. But in general, you can see that the fit between the theoretical function and the empirical values is quite okay. So it means that even if your sample size is 10, you can use theoretical distribution to describe the behavior of your values, although the fit for the smaller sample sizes, the worse fit will be. Okay. So this is actually it about the parametric approach in general. I'll just remind you the general idea that first you use your sample not to calculate intervals, percentiles, quantiles, and so on. You use your sample to calculate parameters of theoretical distribution, and then you use parameters of theoretical distribution and specific functions like CDF and ICDF to do all the computations, to calculate all the intervals and probabilities. Okay. In the next learning sequence, we will talk about very important theoretical distribution, which is called normal distribution. But that's it for now.